Okay, so let's evaluate the double integral here. So we have the integral over the region D, and we have y over x squared plus 1 dA, and our region D is the region of xy values such that, this means such that our x's is from 0 to 2 and our y is from 0 to x squared. Oh no, x squared. Sorry, x to the 1/2, which is square root of x. 0 to 2, 0, yeah, that's right. So really, if you wanted to, you can draw the regions. I'll draw it out. So we have y, x, and our x's range from 0 to 2. So x is 0 is this line, y-axis. X is 2 is 1, 2. This line here. Y is 0 is just here. And square root of x is, how does the square root of x look? So the square root of x, if you forgot how it looks, because I'm kind of blanking out, is going to be 0, 0, 1, 1, and then 2, let's 4, so let's do 4, 2, so it's going to be 1, 2, 4, 2, and so on. That gives you the general shape. You don't really need to go on. If you want, you can go to 9. It'll go 9, 3, and so clearly the x is increasing while the y is not increasing as much. It's like that. So our region is very evident here. It's just this region that I will shade in blue. It's not a necessary step to do this, but it's just fun to do it sometimes, just to graph it out. Now let's go ahead and fill up our integrals. So we're going from something to something, something to something. Remember, the constants will always go towards the end. So the x is constant, so it's 0 to 2, and then the y, so it's 0 to the square root of x. So we have our y over x squared plus 1, and then dA becomes dy dx. So that we can first look at this one here. So that's going to be the 0 to the square root of x, y over x squared plus 1, dy dx. It's not that hard to evaluate this integral given that oh sorry, not dy dx, this is just dy. It's not that hard to evaluate this integral given that it's with respect to y, not with respect to x. And so basically, even if it was with respect to x, I don't think it's that hard. But you can take this 1 over x squared out, x squared plus 1, and then you would integrate, so it would go from 0, y squared over 2, going from 0 to the square root of x. Simple as that. So that just becomes 1 over x squared plus 1, and then I'll just multiply the 2 out as well, so it's going to be 2x squared plus 2. And then it'll just become y squared, which is the square root of x squared, which is x, minus just 0. Doesn't matter. So this becomes x over 2x squared plus 2. This nice stuff is what goes into the white line that we have there. So running out of real estate, it's a problem. I'll take my region and move it. Let me take that. Oh no. Okay, that's better. So to continue, we'll end up with the integral from 0 to 2 x over 2x squared plus 2 dx. This is not too hard to do. We just set u equal to 2x squared plus 2, du dx is 4x, just 4x. So du, we multiply dx on both sides, is 4x dx. Given this information, we can input or get in a 4 and then a 1/4, because we don't want to change the value, so it's just 1/4 integral. Plugging in 0 here, we have 0 squared, 0 times 2, 0 plus 2 is 2. 2 squared is 4, 4 times 2 is 8, 8 plus 2 is 10. And then we have 4x dx, which is du, over 2x squared plus 2 is u. This is awkward, I'll just write it like this, 1 over u du. Okay, so this is just 1/4 times the natural log absolute value u, going from 2 to 10, which is 1/4 times the natural log. Don't really need the absolute value, but it's there. That's our value right there. And really that's it. I'm running out of room, so I'm just going to leave it like this. This is our answer. You can't really do much anyway. This is a good enough answer, actually. So what does this represent? It represents the area, the volume under the surface here over the region here. That's it.